Hi, I'm Metta Spencer. Let's talk about concrete again. It's really important stuff. You know, it's the most common building material in the world, or material being used for anything, I guess. And it creates something like 8% of the emissions that have to worry us of carbon dioxide. So this is a big problem. But the blessing is that if we do it right, we can turn it not into a liability for the world, but a real asset, because you developed correctly and used correctly, concrete can actually capture and sequester carbon and lock it up in large amounts. And because we use so much concrete in the world, we could lock up a heck of a lot of this stuff that we need to get rid of. So it would be a major factor in reducing climate change. And that's why we need to talk about it. So what's going on now is that the Canadian Pugwash Group is holding some, let's call them inquiries, into various possible ways of reducing the problems of climate change. And one of the methods that we're considering, we're just discussing it and talking and trying to get smart about it, is the use of carbon negative or low carbon concrete. So I have some experts with me today, some people who actually do some of the real work. They know what the stuff looks like and smells like, and they can pour it if they have to, and they really know their stuff. And so these are civil engineers in various parts of the world who are going to give me a very up-close consideration of concrete and how it can be used in the world. And my friend Adele Buckley will be joining us, and possibly one or two other members of the Canadian Pugwash Group, to help me interrogate these fellows. Okay, so first I want to introduce Adeyemi Adesina, or Yemi, who is a material scientist and civil engineer who works on developing cheap and sustainable building materials. He's been working and collaborating with people in 11 different countries on 4 different continents. So good morning, Yemi. How are you?
I'm good. Good morning, everyone. Nice to be here.
Good to meet you. And in Cambridge, or I don't know, you're not really in Cambridge, but you are, I think you're based in Cambridge, is John Orr, who's a professor of engineering at the University of Cambridge in England. But he said he's going to be in Lyon, France, consulting today. Where are you today, John?
Morning, Metta. I didn't make it to Lyon because we've had some snow and it's not been possible to travel from London today. So I'm in London.
Oh, okay. Well, we have snow here too. London doesn't get much snow normally, does it?
No, that's why the transport system has fallen down.
Oh, yeah, okay. Well, anyway, I'm glad that you can join us. And here closer to home for me in Toronto is Ryan Zizzo, who's the Chief Executive Officer of Mantle Developments. And I was talking to him over the weekend, and he said he goes out and he and others, I suppose, go out and advise architects and builders, consult with them on how to design low carbon or buildings that are sustainable, and especially using low carbon concrete and so on. And now my friend Adele Buckley is here as well. She's not an expert on concrete, but she's an expert on just about everything else, because she's an engineer and a scientist, and also a very important activist in the Pugwash movement. So Adele will no doubt have pertinent questions to ask. So hello, Adele, how are you?
Well, I'm well. I unfortunately haven't followed all of the concrete discussion, so I may ask uninformed questions, but I hope to participate.
Okay, now here's what I have in mind today. We've had a couple of conversations about concrete with mostly from well, from way above ground, theoretical more. And I think that all of you as engineers actually have practical considerations that you probably talk about, and you can share with us. Let's say you happen to all meet in a bar after a conference. And what would you talk about? Because I know there are many, many developments of new and alternative ways of creating concrete. A lot of them have to do with, I think probably the majority, have to do with alternate types of cement, or alternates to the use of cement, because cement is apparently the major source of CO2. The concrete consists of cement, water, and aggregate, which are sand and gravel mostly. And now they're playing around with other things. Let me ask John first. Why don't you talk a little bit about what you're doing?
Maybe I'll start with what you said about cement. So you're right to say cement is the main contributor for CO2 for concrete, absolutely. And when we talk about cement, we mean Portland cement, and making Portland cement, about half of the emissions of CO2 are completely unavoidable. They come from a chemical reaction when you make clinker. So where my work sits is looking at the scale of cement production. It's about 4.2 trillion kilograms made every year. How can we cut the emissions? And for me, the quickest and easiest way to do that right now is to use less stuff. So when we talk about a hierarchy of emissions reductions, the first thing is use less cement. So that can mean lots of things, which we can come back to. Below that, you can talk about how you specify the material. And below that, even lower, is offsetting. So how do you use less cement? Well, one way to do it is to use less concrete, of course. So you design your buildings to be optimized. You make, how I would phrase it is only use concrete where you really need concrete. Don't just put it everywhere, which is quite common in construction today, because although it's an easy material to make, we should really view it as a sort of resource constrained material because of the CO2 impact of it. And then you go to sort of how you use alternative materials. So you mentioned that as well. So often people will use what we call a blended cement. So they have ground granulated blast furnace slag, or PFA, pulverized fuel ash, and they blend that with the cement. That cuts the CO2 emissions. But the issue there is those two materials are very resource constrained. There's not much of it in the world. And so you can't just say everybody can have blended cement, because there's not enough to do that. And so again,
I never heard of it. So please, if I ask dumb questions, it's always good, because, some of my listeners are probably not even as smart as I am about this.
So they're byproducts from industrial processes. So coal-fired power stations and making steel with a blast oxygen furnace produce these byproducts, which is a sort of a fine powder, which can be blended with cement. And because they're a byproduct, they have lower CO2 emissions associated with them. In the UK, it's very popular to use those materials. But what we do actually is we import it from as far afield as Japan. So it's a sort of a funny sustainability question, where we're making the concrete in the UK better, in inverted commas, by having these blended materials, but we're taking it from places around the world, which means they can't use it. So again, for me, the main thing is just try and use as little concrete as possible.
Yeah, and I'll just add, in the Canadian context, we are having issues with that as well. That one of the main supplementary cementatious materials is called slag, and that's from coal-fired plants. And in Ontario, if anyone's familiar with the Ontario electricity grid, we got rid of our coal-fired plants about a decade ago. So slag is not really an option for us. Just as John said, we would have to import it from other jurisdictions if we want to use that as one of our materials. So we are using other things like fly ash, which is from steel plants, and we do still have steel production in Ontario. But as John was saying, that some of these industrial byproducts are scarce, and it's not like we have an unlimited supply of them.
I totally agree with John and Ryan on that. And again, this brings into place the real definition of low carbon concrete. So in some cases, shipping this material might not be sustainable at the end of the day. So one of the ways to actually achieve this low carbon concrete is to find ways to use locally available material. So for example, if you're shipping your fly ash all the way from Japan to the UK, by the time you kind of estimate the emission associated with the transportation, by the time you calculate that, do you still have a low carbon concrete? Mm-hmm. So at the end of the day, to really achieve a low carbon concrete, we have to focus on the use of locally available materials. So this means that the definition of low carbon concrete is very, very relative. It's very relative to the kind of material you're using. For example, low carbon concrete, for example, using fly ash in India might be more sustainable. But in Canada, here we have less fly ash. In our case, it might not be a sustainable concrete. So we really have to be careful again with the terminology of low carbon concrete.
Mm-hmm. Okay, now what would you do if you want to cut back on concrete, but you're still building things? What do you do instead? I mean, the total amount of concrete is, if you don't use that, you're going to use something else. I've heard people say, well, do more with mass timber. Well, mass timber is also questionable, isn't it?
People have to go for lower costs, and some of these newer concretes probably cost more. Therefore, how can you get the necessary impetus to use the new ones if they cost more? And second of all, I believe that concrete has different specs depending on what you're using. Therefore, if you're trying to accommodate a certain kind of strength, it's a different mix. If you're trying to accommodate certain weather patterns, particularly say cold climates, it's a different mix. And all of these things are constraints. And then I think a major constraint has got to be that there are government regulations which you must adhere to, and if the government regulations have not caught up, or even if you can't use current regulations, how do you develop new regulations that support these better kinds of concrete?
Sure, that this will all come up, but before I switch back to our guest speakers, I want to greet Paul Beckwith, who has just joined us. Paul is also a new member of the Pugwash group, but he is an old friend to me because he's a climatologist in Ottawa who makes lots of videos of his own. He knows what he's talking about. So it's good to have Paul with us. Adele asked a whole bunch of questions, piled one on top of the other. Who wants to tackle one part of it?
I was going to say about the cost. Oh, I think my video is frozen. On cost, it's an interesting one because, yes, concrete is basically relatively cheap because it's easy to make. Yes, a bag of cement is quite cheap. There's an argument, actually, that if it was more expensive, we'd be more incentivized to be more efficient with it, which might be a good thing. And people have talked about things like carbon taxes for decades, and whether or not that will ever happen, I don't know. But for me, it's about the design of viewing it as a carbon intensive material and using as little as possible. Whether the alternative processes cost slightly more, it may not matter in a city like London if the land is so expensive that the cost of the building is relatively small. So it just depends what you're doing, really, what you're building with it. And then you mentioned things like regulations, and again, that is a constraint, but in the work that we've done, what we find is you get in a typical building, there might be wastage in the order of 30, 40, 50% of the concrete could be taken away, and the building would still satisfy all the regulations. So it's a one where we're relatively conservative as engineers, and sometimes that conservatism is causing an unintended consequence, perhaps, with CO2.
So they're just afraid, they want to make sure the thing doesn't fall down, so they use twice as much concrete as they really need?
It's sometimes that. I mean, we are concerned with safety, of course, but it can be things like making all the floor plates the same thickness everywhere, which isn't necessarily needed, making all the columns the same size, which isn't needed, or adding lots of concrete just to form the walls of a building, when you could make the walls out of straw or hemp, which is a much lower carbon alternative, but concrete is easy, so you kind of stick with concrete. So there's lots of ways a designer can think about, how much concrete do I really need and where should it go, and not put it anywhere else. It's a material that's good in compression, not good in tension, so maybe we only use it when it's in compression, and everywhere else we use a different material. But many buildings, if you go around, well, any city really, you see a concrete frame going up. It's concrete everywhere. So it's just thinking about what material should go where, I think, is really important.
Okay. Yemi, you started to speak.
Yeah, just on the point John mentioned, again, one of the things we realized, actually, some studies just came out, is that we have a lot of over-design. So let's say, for example, I'm designing the concrete for a sidewalk. I don't need 50 MPa. I don't need to really use an ultra-high performance concrete for a sidewalk. Because when you use those things, you're using your higher amount of cement, which means more emissions. So in those cases, we should really find a way to prevent the over-design of concrete, which will result in lower cement consumptions. In terms of the specification, I think this is actually one of the main challenges we have in implementing sustainable alternatives. There's a lot of materials that has been developed that actually have good properties, better than the conventional concrete. But the problem is that the design codes and standard we have is called prescriptive based. So which means you need to use a certain amount of cement for this particular design. But in a case where you're not using the conventional cement, what happened in that case? So there's really a push now to have more of a performance-based code than prescriptive. So we just should focus on, for example, if you can get this durability, this strength, yes, you can use this material. So it's always good to go more towards the performance-based rather than the current prescriptive-based codes we have right now.
Okay, let me switch the gears, because suppose the game is to adopt and widely use carbon negative concrete. And I have done 2 shows, one with Brent Constance, who is the head of something called Blue Planet. And I know that he and his company is going into business with Lafarge Holcim in North America to create carbon negative concrete. And it is so carbon negative that you want to use as much concrete as you can, because it's going to absorb, the more concrete you use of this carbon negative kind, the more of the world's CO2 it's going to suck up and lock away. So the name of the game will not be how to reduce the amount of concrete that gets used in the world, but where else we can employ it to good effect. Is that, I mean, now, okay, tell me I'm silly, any of you who think I am.
As a philosophy, I disagree. I don't think in any material that you view as being negative carbon, that should be an excuse to use loads and loads and loads of it. People, the similar argument you made for timber in some people's view is carbon negative, therefore over-specify timber. But that doesn't work on a global scale, because we can't do that. And it's a silly thing to do from a design point of view, because why are you making a really inefficient building? It's sort of philosophically, I oppose that. So my concern, and is this the Blue Planet product that Brent did? Is that right? Yeah. So whenever somebody says it's a carbon negative material, I think we need to really interrogate what they mean and how they've calculated that. And all I've seen is the website, so I'm uninformed. So I'm sure you know more about it than me. But in that process, the Blue Planet process, they are still producing Portland cement, which releases CO2 emissions. So the negativeness is coming from the aggregate and the sand. So I'm a bit concerned that would encourage people to overuse concrete, because, as I said, I just feel as a philosophy, as a designer, we should, to steal a phrase from an old mentor of mine, touch the earth lightly. We shouldn't be overusing resources just for the sake of it. It's not a good approach from my view.
Okay.
Yeah, I agree with that. And also, I think we need to always be looking at the numbers, right? Like sometimes we get swept away with a story as opposed to looking at the actual quantities involved. So I think this might be an example, as John said, like dig into that. There's other examples I've heard of. For example, some companies inject CO2 into concrete mixes. That's something some people might have heard of. And in some people's mind, that means it's a totally carbon zero product because all of the carbon gets injected into concrete. But, again, that's a good story. But when you look into the data, it actually only reduces the total carbon footprint of the concrete by about 5%. So, I mean, I've spoke to some people who, when I try to put the the topic of low carbon concrete on their agenda, they say, oh, we've already dealt with that. We're using concrete that has injected CO2 in it. And in their mind, it was carbon neutral. But I said, well, do you realize that's only a 5% difference? And they said, no, it's not. It's carbon neutral. So sometimes the story can overshadow the data, and we need to make sure we're always looking at the data, the numbers. But the one thing I also wanted to say about efficient design, John gave some really good examples of using less material, using the material more efficiently. But there's a whole other dimension that we can use more efficiently, and that's the curing time. So concrete cures, it gets stronger over time, right? And as an industry, the typical curing length that we use is 28 days, the shortest month of the year, February, so that it's a safety factor saying, oh, allow it to dry for a month or to cure for a month, and then
hold on. You've got to educate me on this, because I don't know a thing about shearing.
Curing. So curing, curing.
Curing, okay.
The more cement you put into concrete, the faster it will cure. So if you want cement to get really strong in a short period of time, then we have to add more cement to it. So basically, as an industry, we say the strength that this concrete is rated for, say 30 MPa, it needs to hit that 30 MPa in 28 days. That's how the concrete designers figure out how much cement they need to put in to achieve that. But if we allow certain parts of the building to cure over a longer period of time, maybe we don't need the full strength in 28 days. Maybe we can have that strength in 60 days or in 90 days. So if we allow certain elements of the building that don't require early strength to cure over a longer period of time, that allows us to use less cement. So that's a way that we can greatly reduce our cement without, if we don't change anything else, just picking out those elements that don't need to be at full strength in 28 days, like foundations and footings. Those aren't going to see their full strength for years, right? Until the building is fully occupied and there's a party and there's a storm all at the same time. That's not going to happen in 28 days. It's physically impossible for those loads to be met. So it really makes no sense for us to require some elements to have 28-day strength.
Mm-hmm. Okay. Well, let me explain what little bit I understand about any carbon negative concrete, and the Blue Planet. I kind of got part of it, and what they do is it's not the cement that they're trying to reduce. It is the change in the composition of the aggregate. And they simply create aggregate by taking waste, demolished concrete, and smashing it and combining it with CO2 and presumably some secret formula, which they get their CO2 from some smokestack that's right next door. They always have to be close to sources, because I gather that the cost of concrete of any kind is largely predominantly a function of the distance you have to move the materials. So they combine these old demolished concrete with CO2 and create aggregates of little pebbles that then they mix with the cement in the usual way. Well, this aggregate is so carbon negative that it greatly offsets the carbon emissions produced by the concrete. But one of the other features of this is they don't necessarily have to do it this way, but they can use the carbon emissions that are produced during the making of the Portland cement. They capture the emissions from the Portland cement and then use it as a part of the ingredients for the aggregate. In any case, the aggregate is supposedly, I've heard the expression 440 kilograms of carbon per, what is it? Would it be a cubic meter of concrete, or I don't know what? But at any rate, it's apparently a stupendous amount of carbon that gets locked up in this aggregate. And that is the approach. Does anybody want to?
I think I'll still go with what John mentioned earlier. So even though the cement is just about 15% the component of concrete, it is responsible for more than 70% of the carbon emission. So let's say we have a carbon negative aggregate. Is that really turning the old concrete to the carbon negative? So we really have to quantify these numbers very well and be careful with what we really call a negative concrete. Because again, aggregate, even though it's a huge volume in concrete, the impact on carbon emission is very low compared to that of cement. So,
well, if I say what I said earlier, when I looked on the website, the numbers that they have absolutely result in a negative value, right? So the numbers are there. What I don't have for my own investigation is an independent review of those numbers. You know, anybody can write a number on a website. So I'm not saying it's wrong, and I'm not saying it's impossible. Yeah. Absolutely, mineralization is a thing, and it's a way to capture carbon. Absolutely, it's the science is there. Yeah. I just haven't been able to look through that in any more detail to really show that it's correct. And the second point I would make is carbon capture and storage has been talked about for a very, very long time. How much is available? I don't think any cement plants are fitted with true carbon capture. There's about 6,000 cement plants in the world. I would say 0 have it or attached to them. There may be CCS attached to other plants, of course, I don't know. So how much can they actually receive from those sources? And then what does it cost? If this process makes the aggregate very expensive, then it actually supports my previous point about using less material, because the concrete's going to be more expensive, and therefore you should be using less, not more. Or you would be using less as a designer and as a contractor, because it's being more expensive.
And I think this is why it's good for any initiative or approach to reduce the carbon emission of concrete to really do a comprehensive life cycle assessment. There are a lot of various promising options to do this. Some of it is actually alkali activated materials. But in some cases, you're using heat curing, you're using sodium silicate, which have a high embodied energy. So even though it's a sustainable alternative to Portland cement, by the time you do a comprehensive life cycle assessment, that material actually has a higher embodied carbon compared to cement. So it's always good to really evaluate, like have a comprehensive life cycle assessment of these sustainable alternatives to Portland cement.
I'd like to add on to that comment, actually, because you may have talked about it before I arrived, but when concrete buildings are designed, or general concrete structures, what is the expected lifetime of these structures? You know, is it like, 30 years, 25 years? I mean, I see a lot of, bridges, for example, concrete bridges where, in Canada, we get the salt on them. We get corrosion of the rebar. We get pieces crumbling. And I'm in Montreal at the conference on biodiversity, the COP15, and Quebec and roads, bridges have been notorious for chunks of rock falling down onto the roads much faster than you would expect based on the engineering lifetime specs. So, I guess that's the question. Shouldn't we be talking about the durability of concrete? Because if it's capturing carbon or not in aggregate, if it only lasts 20 years or 30 years, it's not a very long-term store of the carbon. Unless, I guess, you get mineralization, and so it's just rock that you result of when it crumbles. But why can't we make concrete to last longer? I mean, the Romans mixed concrete rock materials with salt water, built structures in the ocean that have lasted 5,000 years. So their concrete can last 5,000 years. Ours lasts 30 years. So what's the problem? We've forgotten how to make it properly.
Trying to figure it out. so I should also mention that in terms of standard and codes, like for example, a common example is freeze and thaw. Ideally, when these codes were designed to really evaluate the durability, probably you have like a cycle, like maybe you have -5 this week, 0 next week, and maybe again -5. But with the impact of climate change now and everything we're saying, within a week, you could have like 4 different cycles, maybe -5, 0, 10, again -5. So there's really need for us to, again, as you mentioned, to really consider durability and sustainable design. Because again, if your concrete is lasting longer, it means you don't need additional material to repair or to replace. So at the end of the day, it's a sustainable like concrete. So we really have to really consider durability, the sustainability of concrete generally.
Yeah. So I would question the the rationale behind pouring concrete when we have temperatures that could swing, far above and far below zero. So maybe we shouldn't be building or pouring concrete in the spring and fall seasons in Canada any longer, for example. I mean, I've often talked about weather whiplashing, where we go from one extreme to the other, depending on where your location is relative to the jet stream, the meteorological reasons why we're getting these huge swings. But like in Ottawa, for example, they've had a huge problem with sidewalks because of all of these increased numbers of freeze-thaw cycles. So if you're in a city where you are very close to zero, you're going to be swinging above and below it numerous times, maybe 25 times in a month, for example. At night, it always goes below zero. During the day, it always goes above zero. You can have that happening 30, 35, 40 days, in a spring or fall season. When it's in the winter and it's well below zero, it never goes above zero. You're in a different regime. In the summer, it's always warmer than zero, so you're also in a different regime. So are you aware of how much the lifetime of concrete is degraded when it's poured, and experiencing these huge swings in temperature? Because I would expect its lifetime would be severely degraded. Maybe this is part of the problem with concrete structures failing in 20, 25 years when they should be lasting much longer.
Yeah. So I'll say from design perspective, again, we have more of theoretical values for those, but this is quite different from the reality. So for example, in addition to the freeze and thaw, we have corrosion. We are using a lot of salt going on this road, affecting this. So like we have this theoretically, but in reality it's quite different. So we really have to design, we have to have enhanced durability design. We have to find a way to really incorporate this. And right now too, we have material that are very durable that can be used for this application.
Affecting the durability of the concrete. Is it the climate? Is it the salt? Is it something else? Is it the quality of the materials? And is it known in advance how a structure is going to last before you pour it? And what Paul was suggesting was that maybe it makes a difference whether you pour the concrete in warm weather or cold weather. I don't know. This is all a complete mystery to me.
So the first question you asked was about design life. So typically you would say more than 50 years for a building, more than 100 or 120 years for a bridge, right? So we do think about design life. We want our stuff to last for a long time. And you're absolutely right to point out that the Romans, the Pantheon is still the world's largest unreinforced concrete dome in the world. And that's 2,500 years old. But the key thing there is unreinforced. So the issue with concrete is you put steel rebar in it, and the rebar corrodes, as was just mentioned. It rusts, it expands, and it makes the concrete crack. And then, as you said I think you said Montreal, you see the bridges are starting to deteriorate. Bits of concrete are falling off. So that was probably very much related to when the bridge was designed, likely 1960s. I think there's a few famous bridges in Montreal from the 60s, which are sort of deteriorating. So what you have to do with concrete is you have to protect the steel from rusting, right? And you do that by having what we call cover, the distance from the steel bar to the outside world. And you think about how permeable the concrete is from the outside world going in. So that things like salts and chlorides and other deterrents don't get into the concrete. But it's the additional steel which is the key problem. Concrete on its own is fine, as we've seen with the Roman stuff, but the steel rusts. So what we do now is we think carefully about how you protect the steel, or even, and this does happen in Canada, I think, you use alternative materials like fiber reinforced polymers, which are basically plastics, which don't corrode and therefore don't suffer the same problem. So you're absolutely right to point out that, some historic uses of concrete haven't been so great, and even maybe modern ones haven't been so great, but we do know that that's an issue, and it's really the job of the designer to try and prevent that deterioration from happening. And just final point on design life, 120 years isn't that really that long in terms of a city. And I would really hope that we were designing for much, much longer than that. And that might then again question, should you put steel in concrete? Maybe the concrete should just be sort of compression only structures, arches, vaults, without materials which are going to corrode over time. So again, it's about thinking what's the material really good for and where should the material go?
Oh, well, now how about reinforced concrete being abolished? I mean, I assume that the thing hasn't been even used except in the last 50 or 100 years. And now it's in everything, isn't it? Could you, I mean, I'm in a building now, 23 stories tall. I hope they've got steel in this concrete. I'm not sure. But it could, are you suggesting that you could still go ahead and build a building like this without without steel reinforcement?
It'd be very difficult to build a concrete building 23 stories tall without reinforcement. So I think what I'm saying is, as a designer, think very carefully about what you do in terms of detailing to either protect that reinforcement or to use something else, build it out of timber. There are other materials around.
Yeah, there are timber buildings that are over 20 stories actually, and we're seeing a strong direction towards more and taller timber buildings. But we can also create more innovative new solutions that still use concrete, as was said by John, in compression, but have another material for the tension, and that other material isn't covered by concrete that's going to degrade. So, there's some composite material elements that have concrete on the top, and then they might have like a fiber material in the tension without concrete covering it, or something that's not going to erode. But just to go back to Paul's earlier point about the freeze-thaw cycle, my understanding is that it doesn't matter when it's poured. It's not about this freeze-thaw happening during the curing time. It's just about the concrete degrading over the life of it. So just to make that point clear, it's freeze-thaw. It just impacts the concrete. It just accelerates its degradation at any time of year. It's not about being poured during a period of freeze-thaw. So that, I just wanted to make that point to clarify.
There are a number of large companies who do construction, and I know that they have all sorts of questions of design to consider when constructing, but is there any possibility that all of them would decide to include low CO2 content as one of their criteria? There's so many other things that I've heard you talk about that it seems to me that I don't sense that the industry as a whole has decided that it should do this, and so they have to do it. It doesn't just have to exist as a process that can be used. It has to be that everyone in the industry decides we're going to do it. And even if it's now imperfect, if it's just part of the regular way of doing things, I think gradually over the years, it'll probably get better. So what makes anybody decide to use it?
So I can comment on that, and you're right. Most people aren't doing this right now. This is very much a nice to have, not a need to have on a lot of people's agendas, but that's changing. In 3 weeks, when the clock turns to 2023, the federal government of Canada's new embodied carbon policy will kick in, and all federal construction projects as of January 1st onwards will have to quantify the carbon footprint of their concrete and show that they're 10% below a typical concrete mix. So this is just going to be brand new in 3 weeks. It applies to all federal construction. And then they have the plan to add structural steel as a new material that the similar assessment will have to be done in 2024. So it starts there at the federal government, and then it's going to trickle down to, provinces or municipalities that will adopt this, and then, best practices of various construction firms. So we're at the very early days of this. You guys are all ahead of the curve to even be asking these questions, but I like to tell people in 5 years or 10 years, this is going to be a requirement for your building permit, right? It's just hasn't been on the radar up until now. When I started my career as a green engineer 15 years ago, we were having this discussion with energy modeling. It was only the most advanced projects that were going for LEED certification that did an energy model. And now it's every project basically does that to get their building permit. So I think we're at the same point with life cycle assessment and low carbon materials, that right now it's the leaders doing it, or people in a very, stringent jurisdiction that, if Toronto wants to lead and make a requirement for that. But over the next 10 years, we're going to see this trickle down to become a standard part of construction.
I just love that. And in fact, the first show I did, we had Doug Hooton, who's an expert from the University of Toronto, retired now. And he basically told me, the project that Pugwash is doing, which would, if we investigate things, we would wind up recommending to the government of Canada that it require in the future that all of the concrete that it pays for its own funded infrastructure should have to be low carbon or carbon negative concrete. And he said they've already passed legislation basically to that effect. So yeah. The good news is that we're way behind the curve. But at any rate, that's one of the things that we will still have to look at to see whether or not what kinds of recommendations Pugwash wants to make. But I had one further thought, which is that I'm only learning a little bit because I don't have any background as a scientist. But as I understand it, the concrete, once you've created a building, that or a sidewalk or whatever, that concrete continues to absorb CO2 from the air around it. Is that correct?
Yep.
So even if the thing gets old, is there a point where it's saturated? Is there a certain curve at which it absorbs CO2 and then it gets all full of it and it can't accommodate anymore? Or could you do anything to make the structures that you pour continue to grab more and more concrete and hang on to it longer?
Well, so concrete does carbonate. So CO2 works its way in from the outside world into the concrete. But as a designer, what you try and do, what you need to do, is to prevent that carbonated layer reaching your steel reinforcement. So again, it goes back to that steel, that once the carbonation reaches the steel loses its passive protection from corrosion. So yes, it does carbonate, but it's a very slow process. And you actually don't want it to go too far into the concrete when you're using steel. So yeah, that's the quick answer. It's not really a process which sucks up much CO2 in my book. I don't think it's something we can rely on.
Okay, but the system that's operating, the scientific process, is the same for two of the measures that Pugwash is considering. One of them being rock weathering, enhanced rock weathering, where we powder. The idea is to powder basalt and other kinds of rock and spread it on soil, not only to make the soil more fertile, but also because powdered rock has more surface area and will absorb more CO2, and therefore it becomes a significant measure for reducing climate. But presumably, if you took old concrete and smashed it up and spread it on the soil, might not do anything for the fertility of the soil, but it would have the same effect as we're talking about using basalt and other kinds of rock. Is that right? The principle is the same.
The principle is the same. If you break up a concrete beam into rubble and spread it out on a car park, it will suck up more CO2. But you need to leave it there for quite a long time. And I don't think it's really feasible in terms of volumes to have vast swathes of the land covered in concrete rubble. I don't think the society would be very happy with that.
Yeah, and it's reabsorbing some of the carbon that was released during its production, right? So it's never going to suck up more carbon than it was used to make it. So it can never be a net negative. It could, if it was 100% effective, which it isn't, but the most it could ever reabsorb was the amount that was emitted when it was created from the chemical process part of it, not even from the fuel that got for the heating process. So it would never be a solution to reverse climate change, for example.
Mm-hmm. But the basalt could be, but I think probably the level, the amount of CO2 that it can absorb is not comparable to the really extraordinary amount that the Blue Planet people claim that they are able to absorb. and retain, lock up in the concrete that they make. Ryan, you've looked at the numbers, right? They are making.
I haven't actually. No, I know about the process, but I haven't done any kind of third party.
I guess John looked at it, right?
No. What I said, Metta, is I looked at their website,
Yeah.
and I haven't seen any sort of third-party review of those numbers. I don't know if they're. Yeah, I don't know enough about what they're doing to say if those numbers are correct. All that I've seen is that they are negative.
Let me.
Okay. Can I ask a couple quick questions, Metta? For concrete structures that are going below sea level, okay, for causeways, etc., are they still reinforced concrete, and do they do something special to them to keep ocean water seeping in and corroding the rebar? And also, how good an insulator or conductor of heat is the concrete? So, when you have a bridge and do you get an unequal temperature distribution within the concrete? And if you have multi-phase concrete, so you have put rebar in it or some other substance, there's going to be different thermal expansion coefficients of these materials, and that's going to cause cracking and causing seepage of that's going to be exposing rebar or whatever's in the concrete to the external environment quite quickly. Most concrete does crack to some extent. And, I'm concerned about Florida. We had an example of a concrete structure on the beach and, with tidal surges, et cetera, tropical storms, where you get storm surges, the bases of these buildings are under sea level, under seawater for, weeks at a time before it dries out. And then we've had some building collapses on coastlines of Florida, probably because of the foundations being undercut by the flooding from storm surges. So I know there's a lot of questions in there, but those are all related to the deterioration of concrete because of climate and weather events, et cetera, exposure to seawater.
I mean, I can try and tackle a few. The thermal coefficient of steel and concrete is about the same, so there's not a differential between them. Concrete does have a high thermal mass, so it's like stone, so it's a massive material, which is good if you're in a building, so you can use that property to help you with sort of natural ventilation, heating, cooling of a space, because it sort of dampens the changes in temperature over a day. So that's a really useful way to use concrete. You mentioned about a bridge deck having a gradient of temperature across it. It does, as does any bridge, like a steel bridge, because the top surface is exposed to the sun and the underside isn't. So you can see how that's going to happen. It'll be cooler underneath. And then in design codes, there'll be all sorts of temperature profiles that people use to work out what's the effect on the structure, which will be considered by the designer. So yeah, those are the three I remembered. Sorry.
Okay, thanks.
I think we're running out of time, but I think I have a burning question that I just want to put before us. When you talk about the data that Blue Planet puts forward, I think they need, and the industry needs, a process known as environmental technology verification, with which I have had a lot of experience. And essentially, the data that support whatever claim you're making is examined in specific processes by a third party. And therefore, you actually can take confidence in the data or not, depending on what happens. So I think a third party needs really to examine their data and do that. And now there are government backed processes in Canada, the US, and Europe, at least, to do that. Anyway, that's what I think Blue Planet needs in order to be credible.
Okay. I can't recall exactly what they say, but I remember something like this, that the amount of carbon that they expect to lock up is something such that if 16% of the concrete being poured in the world were made of their concrete, it would handle all of the current emissions of human CO2. So it would handle all of our all of our climate problem, something like that. It was just an astonishing figure. I didn't think that I should have to be able to quote it, so I didn't look it up first, but I'll tell you what I'll do. I'll put it in the comments section, because when we post this video, which I'll do tonight on our website, there's a place that people can discuss it below, a comments column. So you guys can put any further information you want to add in that comment column, and anybody watching this can go there and I will have the exact quotation that they claim. Now, if Adele is right and they need to have a third party and investigate it, of course, that I can't answer for that. But I can say that one of the things I want to get in one of these shows coming up soon is somebody from Lafarge-Holcim, because those two are the biggest concrete producers anywhere, I gather, and in Canada and North America at least. And they have entered into a deal with Blue Planet to create plants to manufacture this type of aggregate in Canada. And I want to get somebody from one of these companies to tell us what their plans are. So I think that Lafarge-Holcim would not have entered into this if they find that the numbers are suspect. That's my guess. Anybody?
And to be clear, Metta, I don't think anybody's saying they are suspect, but when I'm asked about these things, I like to see what we call an environmental product declaration, which is an audit of what the actual carbon count is. And that for me is all I'm saying. And I think that's really what Adele is saying also. As I said earlier, mineralization technology definitely is a thing. It definitely is scientifically proven that you can do this. But the numbers for me, I'm not putting my reputation on the line for something I've only seen a website for.
Mm-hmm.
And maybe everybody should be searching for that Roman concrete formula. You know, I mean, I'm not aware of any concrete produced today that uses salt water as the mixture, especially if it's got metal rebar within. I mean, that would be ridiculous. But they did use salt water mixtures to make their concrete. You know, and there's in some of their structures on coastlines that have lasted thousands upon thousands of years. So.
And I'm going to post, Metta, once you send us the link to the comment section, I'll post a new report, or not so new anymore, but last year, the National Research Council published a report on strategies for low carbon concrete that is written for a non-technical audience. So I'll share that so that everyone can review it and refer to it.
That's very, very useful. I've seen references to things that were really offbeat. One paper was talking about adding biochar to concrete. That sounds pretty far out to me. Does anybody know anything about that? No?
So that's basically adding charcoal.
Right.
I mean, that would really weaken it, I would think, unless it was very finely ground. You know, because we haven't talked about sand. I mean, sand, is sand all equal as far as concrete goes? I mean, whether it comes from the ocean, whether it comes from, crushed rock. I mean, it's one of the highest volume things that is being mined globally, that people don't think too much about, just basic sand. Mm-hmm. People even talk about shortages of sand.
Yeah.
Well, we're already over time here, so I don't think we can get into all the other material.
But it's time to go. Yeah.
Well, it certainly is interesting, and I'm open to hearing about novel ideas, although this has been I think a very conservative bunch of people, because what you're saying is just be careful. And
no, I think, Metta, what I'm saying is not conservative at all. I'm saying use much less concrete, which is very far out. People don't like that. They don't tend to do this. Cutting your concrete use by 50% would cut cement emissions by 50% and cut our demand for sand by 50%. And we can do that right now with all the technology we have already. So actually, I'm not being conservative at all. I'm saying we've got lots that we can do right now, which will have a huge impact on CO2 emissions. And that can happen today.
Is that more or less conservative than proposals like, there's one that I'm trying to reach a guy to be on the show. He's talking about using algae in concrete. And I think it's not just algae, but it's also little microscopic critters that have carbon shells or something. So, there are a lot of very far out ideas being considered. I would consider yours pretty conservative, John, in comparison to that and to the biochar notion.
Well,
always think about scale. Can you reach the scale that you need? If you can make 1 cubic meter of algae concrete, and I know nothing about it, 1 meter cubed of this idea, it's not making any impact on a global scale. So it has to be something which can be done globally. But we should always encourage wacky ideas, because that might just be the solution to climate change. You never know. So
exactly.
Okay, this has been fun. Thank you very, very much.
Okay, thank you. Goodbye.
Thank you.
Bye-bye.
Take care. Bye. Project Save the World produces these shows, and this is episode number 532. Watch them or listen to them as audio podcasts on our website, tosavetheworld.ca. You can also share information there about 6 global issues. To find a particular talk show, enter its title or episode number in the search bar, or the name of one of the guest speakers. Project Save the World also produces a quarterly online publication, Peace Magazine. You can subscribe for $20 Canadian per year. Just go to pressreader.com on your browser, and in the search bar, enter the word peace. You'll see buttons to click to subscribe.